Thank you so much. So I would like to thank the organizer, to Brigitte, to Roland, and to David. Thank you so much. I really enjoy Vienna. And I loved all the places I've been in Europe so far. So I don't know, maybe it's a sign. So let me talk a little bit about a very recent project, actually, that we started recently. So this is joint work with Sebastian, which is here, and a postdoc of Sebastian. I think I'm going to pronounce it incorrectly. So it's Martin, that's I can pronounce. And then it's Spitz. Is this correct? Good. Okay, so I'm going to talk about modified scattering for the three-dimensional Maxwell-Dirac system. So I'll start from the beginning, meaning that I'm going to consider so for now, I'm going to just tell you what the unknowns are, basically, and I'm going to give you an equation that you will not make sense right away. I'm going to explain all the things that come into this equation in a second. So the first thing I want to say is that we are working on a Minkowski space-time. So we have one space dimension for the time and three spatial dimensions. And then we have the spinor vector field, which is the psi, which takes values from 1 plus, from r to the 1 plus r, and is going to land on C4. So that's complex. So those are vectors in C4. And then we have the electromagnetic potential, which we call it A mu. Let's see which one is the pointer. We call it A mu. And having those two solutions for the Maxwell-Dirac system, I'm actually going to write the system, the Maxwell-Dirac system, in this Lorentz gauge invariance that you are going to see in a bit. And the equations are going to look like this. So I'm going to explain in a bit who this gamma mu is. But this is going to be the Dirac equation that's satisfied by the spinor field psi. And then you have the wave equation that's going to be satisfied by the scalar electromagnetic potential A. And you see here you have the coupling that happens between those two equations. And then here I put in the same color. We are making sure that we are going to be in the Lorentz gauge. And so I carry this equation in blue. So this is a divergence, both in space and time, that we impose on the electromagnetic potential, so that divergence should be 0. And so this will be the system that we are going to work with. And so because we are going to look at global solutions, I need to prescribe, I need to give some initial conditions. So I'm going to choose to give them at t equals 0. And the only thing you should remember from here, psi 0 is common. You already know this kind of notation for the initial condition. But here, because A solves a wave equation, I need to give you both the initial position and the velocity. And so the only thing you should remember is the way we denote this initial data. We have this small a. So don't confuse with the small a that Daniel had in his talk, which was a symbol. Here's just a value evaluated at 0. And so the dot counts for giving you the velocity, the initial velocity. And so I'm going to go further, and I'm going to explain the things that I did not explain yet. But before doing so, I should tell you that we are using the Minkowski metric, which is commonly given by this diagonal matrix. So I'm keeping alpha and beta, the notations down here. And so I have -1 and then 1 on the diagonal. And this admits an inverse metric, which you should be careful. We put the indices up, alpha and beta, but the matrix will going to look exactly the same. And so I'm going to tell you a little bit the convention. So we have the rectangular coordinates, which we're going to call them, when we refer to x, we are basically going to refer to a space-time position vector. So the first one, we call it x0, but you should think of it as the time. And the rest is going to represent the position in space of the vector. So we are going to use this notation x alpha, where alpha is going to run. So everything that's Greek is going to run from 0 to whatever. So it's going to include the 0. And in this case, from 0 to 3, because that's the space we are going to work in. It's 1 plus 3 dimensions. And so if we are going to use normal letters, like not Greek letters, we are going to not take into account the 0. And then what else I should say? We are lowering and raising the indices based on using the metric. So this is a covariance. This is a covector. So the covector is you are taking the vector and you are contracting with the metric. And so you can do this both ways, lowering and raising. And what else I should say? Oh, I should say that we have the Einstein's convention, where if you see more, repeated indices, means we are summing over those indices. So now I'm getting close to explaining everything that's in that system. So we have associated to this metric G, you are going to have those complex valued matrices gamma mu. And like I said, mu is the Greek letter, so it's going to count from 0 to 3. So overall, we have 4 such matrices. And I wrote here the gamma 0, which is formed by those blocks identity, two-dimensional identity, and then minus the identity. And then this one, gamma j, has this form here, and those are the Pauli matrices, this is sigma 1. And so you have sigma 2, sigma 3. Don't bother to remember those. They're going to matter when you do estimates. So you're going to need this anti-commutation relation that I wrote in here. So if you have 2 different indices, this is going to be 0. Otherwise, you're going to recover the metric. And so this is something very useful when you do computations. And now I want to give you so this explains a little bit the gammas that you've seen in the equation, in the Dirac equation. And now I want to introduce something about the notation. So I did not explain you all of it. Like if you look here, I told you what gamma mu is. Still, I did not tell you what the bar is. And the bar is not your common conjugation. It's a little bit more. So giving a vector function psi, so your spinner, which takes values in C4, I'm going to define this conjugation operation, and I'm going to use those gamma mu. So when I'm going to put psi bar, I'm going to actually refer to the Hermitian adjoint. This is this psi star. And I'm going to multiply that by this matrix, by this vector gamma matrix, gamma 0. So this is going to give you another vector as well. And now you can extend this definition, because this definition, apparently, this conjugation operation just works for vector, but you can do better than that. You can extend this kind of conjugation to more general matrices, and I'm using here kind of abusive notation, general matrices gamma, not necessarily those ones, just general gammas. And so then when I'm going to take the conjugation of a matrix gamma, then I'm going to multiply also, so this looks similar, but I'm going to multiply to the left as well with gamma 0. And then one important property that will also play a role when you do computations, and I can tell you exactly where, this is something very useful. So when you take this conjugation operation to any gamma alpha, where the gammas are those ones this time, then that's going to give you gamma alpha that you know of. So those are interesting things that you might know already, but in order to do any kind of analysis, you need to know how this works. So now let me give you couple of introductions. So something about how this Maxwell-Dirac equation came about. So this is an equation, so it comes from an Euler-Lagrange. This is the Lagrangian, Euler-Lagrange equations. This is the Lagrangian that's describing. So then once you have the Lagrangian, you can write down the Euler-Lagrange equations. And so let me tell you what this is. This is shows you the interaction between this connection 1 form, A mu, so this is your electromagnetic potential, and then you have a spinor field mu, psi, and then this shows exactly how the interaction between those two quantities is going to happen. And here I put in red the mass, and the reason I put it in it's because our equation has mass in it, so it's Maxwell-Dirac with mass, so it's massive one. And throughout the computations, you are not going to see this M popping out, because I just decided that it should be 1. So I'm not going to carry it, put it with red, because it matters if you really care about it, but it doesn't change the analysis. It's just something that I'm going to carry about. And here I want to mention that this inner product that you're seeing here is the usual inner product that you would have in C4. So once you have this, you can write the Maxwell-Dirac equations, and I wrote them in here. Right away, you can just write Euler-Lagrange by using this action equation, this action functional. And once you write them down, you're going to get this system, which is not exactly the one you've seen before, because in there I use the Lorentz invariance. That's why you have it in that shape that you've seen it before. So here, let me explain you. This is a curvature 2 form that you see in here, and the other equation is basically, this is the Dirac operator that shows up. And so this follows right away, but in order to get the equations that I showed you before, you need to make a choice on a gauge. And so ours was this Lorentz gauge. And so those are the equations. What do we do with them? Before we decide what to do with them, we should decide on things that we know about those equations. First of all, I'm going to look at the scaling. Though we are assuming we do have mass, which we set it equal to 1, That's the reason you don't see the mass popping out in here. The mass was somewhere in here, and it's 1, so I did not bother to put it in. Going further, let's focus on the scaling. I'm going to still have a scaling, a moral scaling, the scaling that I'm going to get from the massiveless system. So that will play a role. It's going to be my guidance in deciding what kind of regularity should I be aiming for in terms of proving my local results and my global well-posedness results as well. So if you look at the scaling, this tells you that in dimension, spatial dimension d equals 3, we should have that the critical Sobolev space should be what we call this H0 script, which is L2. Here I measure the psi. And then for the A, for the electromagnetic field, I should have H homogeneous 1/2 cross H homogeneous minus 1/2. It's both the position and the velocity. So this is the space that will be interesting to look at. And then I have some conservation laws, and I made an effort to put them in here, though they're not going to make any impact in the way we're going to prove the problem. They're not, first of all, this doesn't have a sign. The energy doesn't help us. And this other one, again, it doesn't play a role in what we're going to do. The first is cold charge, so it's just the L2 norm of the spinner. And this one is the energy. And the only thing that you're going to make use of is this terminology. When I'm going to talk about Maxwell-Dirac, and I'm going to say it's charged critically, I'm going to refer in d equals 3, I'm going to refer that the charge, which is the spinner, this is the critical quantity. And this, it's energy critical in d equals 4 means the energy is going to be critical. So you're going to measure psi in H homogeneous 1/2. And so those are the things we do know about this. So now coming back to the gauges, and I'm going to make some comments based on the possible gauges one can make. So first of all, a gauge invariance means that if I give you a solution to the Maxwell-Dirac equation, then any transformation of this sort is going to also be a solution where this chi is going to be a real valued function that takes values from the time interval I and R3, and then is going to give us some value. So this is basically also a solution. So I'm taking away the differential of chi from the electromagnetic potential, and here I'm rotating the spinner. And this is also going to be a solution. Now, I do have potential gauges that I can make. I can use Lorentz gauge, which is basically assuming that I have full divergence space and time of the electromagnetic potential equal to 0. I also can make this column gauge, which has its perks. Personally, I did not work with it. So it's just assuming that the spatial divergence holds. So this is equal to 0. And you can also have this temporal gauge where you only assume that at the initial time, your A is equal to 0. So those have potential usefulnesses in different contexts. For us, Lorentz gauge is going to be the one that we're going to stay with. And so let me give you some hints. First of all, why we choose Lorentz gauge. So first, it eliminates the ambiguity. You might have ambiguity of having a class of solutions. And like I said here, but any gauge will, because you might have a class of such real valued chi's that will satisfy this, and you doesn't mean you are eliminating that ambiguity. So then, and like I said, any other gauge is going to do that for you. It's going to cut the numbers of potential solutions you're going to look at, but you're remaining with the class of solutions. And here I'm kind of singing some praises to this Lorentz gauge, meaning that I'm saying, oh, for us, it really works because the resulting equation, so pay attention, it's the Maxwell-Dirac, and I put the star. If you remember, the star also included this blue condition. If I go back in, this blue condition, which was basically the Lorentz gauge. So I'm assuming I have the system, which you can very well drop this because you use this to write those two equations from the previous system. But I put it in here because I want to keep it because it will be useful to keep it for later on. So that's why I call the star, in which I'm also taking the divergence 0, the divergence free thing. And so going back, I'm saying, oh, for us, it's very interesting to use the Lorentz because it's a more symmetric form. I'm treating both the time and space equally, and it's giving me a nonlinear wave equation. Compared to a mix of hyperbolic and elliptic, if, for example, you deal with the Coulomb gauge for it, that's a choice. So plus, my equations are going to be Lorentz invariant if I'm gonna do this gauge. I'm gonna choose this gauge. And now I have this comment in here, which basically closes this ambiguity that I was telling you about in terms of the gauges. So I do need, so first of all, I can look at the system that I showed you initially. I can look at it and forget about this blue condition, the divergence free, and I can get a solution by imposing some initial condition, and then no ambiguity is gonna be made. But at the same time, if I'm taking into account this Lorentz gauge condition, so the divergence free, so all three equations happen, then I wanna make sure that my initial data is going to satisfy this constraint equation, and I also need to show that it propagates dynamically and guarantees that the solution satisfies the Lorentz gauge condition. So there are two flavors with this kind of problems. So so in our case, we are going to make sure that we verify this constraint system for the initial data. And now, what else is known about this system? So we have vector fields, which are associated to our system, and I wrote them here explicitly, translation in space and time, the alpha rotations in X, and I put them here under omega ij, and then I put hyperbolic rotations, you have them in here, and then everything that you see, I put them under the same name, Lorentz generators, and I wrote them like this. So when I'm going to refer to Lorentz generators, just think of omega, alpha, beta, and they include all of the above. And then I put scaling with red that you have in here. The scaling is not quite something we are going to make use of, at least not for the purpose of this talk. And now I'm going to make some comments. So I'm going to denote, so if you're going to read our paper, that hopefully it will be up soon. Anyways, in the talk, I hope I'm going to have this notation, which is gamma. And gamma, I'm going to refer to all vector fields that are associated to the linear problem. So I'm putting all derivatives and vector fields all in it, and I'm going to refer to it to gamma. And now when you're going to see the statement of the result that I'm going to just show you, the main result we have, the main two results we have, I'm going to, very bad notation, so follow me. This is gamma, but it's not the gamma matrices. Now it's a multi-index. So I change faces in a second. So this gamma, as you can see, it's a multi-index which is formed out of two guys. And those two guys are basically telling you how many derivatives, regular derivatives you have, and how many vector fields you are applying. And this H that you see in here is basically a balance between vector fields and regular derivatives that you'll need to use when you do Kleiderman Sobolev embeddings. So this is something more technical. I'm not going to get into it, but pay attention. Sometimes this gamma has a different meaning. If it's not clear from the context, ask me. So now, a little bit more about the context. So what kind of energy functionals we should look at, and about what kind of function spaces we should look at. So basically, it's always the case that you look at the linear problem, and you derive from there the conserved energies, and based on the conserved energy, you're going to decide in which space you should work. Though, as we have seen in quasi-linear problem, that's not the smartest idea. It works with this one because you need to change your energy to adapt to your equation, which is nonlinear. Here it's a semi-linear problem, so we are not far from the truth. So it's an okay. We don't need any changes for the energy we're going to assume. So if you look at the conserved energy, you're going to see conserved energies is like you've seen it before. It's sin L2, and then I measure A in age homogeneous 1/2, and the derivative of A with respect to time in age homogeneous minus 1/2. And then associated to this is going to be what we call this Sobolev space, which is this age round 0, which basically tells me that I'm going to measure the spinor and the electromagnetic potential in the right energy spaces that you've seen before. And now if I'm talking about higher derivatives, it's going to mean that I'm going to look at higher derivatives that are piling up on the spinor and the electromagnetic field, but I'm going to measure them in the H0 norm. So, and here I just described the notation that if you worked on the wave equation, you might be familiar by now. So when I call A, and you have this straight letter, straight bracket here, it means you're looking both at the position and the velocity. So now going further, what are the things, now that you have seen it, all the background about this that we needed for this Maxwell-Dirac equation, let me tell you what are we going to answer today. So today we are going to answer two questions. We're going to look at the nonlinear massive Maxwell-Dirac equation that you've seen. We are going to assume we have small and localized initial data, and we are going to prove global well-posedness in a low regularity setting, and we are going to derive an asymptotic description for the global solution, which is going to show us that we do have not the regular scattering, we're going to have something which is known as modified scattering. So first of all, you can ask me, is the global well-posedness in low regularity is new? It is new. It's a little bit, so it's a nuance with what has been done, and I will get to that point. But in terms of having a actual first result, this asymptotic description was never actually given, and it's surprising for two reasons. One is because we get a modified scattering, and you get it for a semi-linear problem, which is not expected. Usually you get modified scattering for quasi-linear problems. Second, it's the analysis is the way we do it. It shows you that you can do. It was not proved before. There was a result, I'm going to get to it, that proved some decay bounds, but there was no asymptotic description whatsoever. So let me tell you what the statements, those two main claims I made in here, they both come separately in a theorem. So let me get there. First of all, the first is the global well-posedness. So I assume I have my initial data. Remember, I told you to remember that this is the electromagnetic potential evaluated at time equals 0, both the position and the velocity. So I have my initial data for the Maxwell-Dirac system, and I assume it satisfies the smallness decay condition, and I wrote it in here the way you see it here, which looks scary. So this is something that I assume is small. But I want to make the following observation. First of all, we worked hard to make this as optimal as possible in terms of how many vector fields we are using and how many derivatives we are using. So here, we are not going to use more than 3 vector fields and 6 derivatives. So from that point of view, this result is optimal, but it's optimal for us. I don't think it's optimal in the big scheme of things. I think it can be improved, but it will be improved with a lot of work, and we'll lose the presentation because we're going to get stuck in, but it's not set in stones. We might go for lowering the number of vector fields. I don't know how easy that will be, but for now we are using 3 vector fields. And you can see here that this is, so those norms in here are the vector fields and the derivatives applied to the initial data, but at initial time. So this have both derivatives and vector fields. So this are vector fields, these are derivatives at initial time. And we measure this, so we have both initial functions, so psi 0 and a. But here, I want to mention that you can see it's different because we can actually have as well just psi 0 evaluated at at time equals 0, just psi 0 in L2, and this comes from the fact that you're looking at the massive equation. So when you're applying the vector fields, you're going to get the mass alone, the mass term alone. So that's the linear term. So that's why we need to impose this smallness on psi 0 as well, not just with vector fields, but also alone. So, so then if this smallness condition happens, then we claim that we have a global solution, psi and a, that satisfies this bound globally in time, but it has this growth that you see in here. So it is t to this c epsilon. And we claim that this is going to lead us to have those pointwise bounds that I'm going to comment in a little bit. So as you can see here, we get that A, which is the electromagnetic potential, is going to decay like 1 over T, basically. So this already signals something very weird because basically you would expect that if you were to look at the regular wave equation, inside a cone you would expect that you'll have a better decay, and you're not seeing this here. It remains 1 over T. And then I'm also showing, so this is going to signal basically the modified scattering in some sense. For people that are just going to look at the theorem, for example, Daniel will look at this and will say, yeah, you have something fishy happening. So why is that? So, and this is where the fishiness is going to be. This is where you realize you don't have the real scattering. And now here is the bound of psi, which is the common known one. So psi is going to decay like t to the minus 3/2. So going further, so you'd expect better if you were to have a regular wave equation, but that's not the case. Going back to the second thing that I said we're going to prove, it's the scattering. So what we are saying about the scattering, we are saying that we have those asymptotic profiles, and we have two asymptotic profiles for the Dirac equations, which I call them psi plus, psi minus, and I'm going to make a comment in a bit. So those profiles, we have this, and we have for the electromagnetic field this profile. They both are going to be in this C sigma, but sigma cannot be 1 because we don't know, we don't have pointwise bounds for the solutions to which we applied vector fields. And we are going to take, we're going to have those two. We're going to prove that we have those profiles, and we are going to obtain that those the solutions are going to have the following asymptotic description. So inside the cone, I'm claiming that the electromagnetic potential is going to look like this weight here that you will be tempted to believe it's out of nowhere. I should have put t to the minus 1 times this asymptotic profile, but I put it this weight in here just because I wanted to keep it Lorentz invariant, and this is very helpful for the computations. So we have that A decays basically at t to the minus 1 times this asymptotic profile plus something that decays better than t to the minus 1. And similarly for the psi, we have an asymptotic description. And again, we use the same Lorentz invariance weight in here, t squared minus x squared. It decays like t to the minus 3 over 2. And then you can see that we have this log factor that shows up in here. This tells you that we don't have a real, so it's a modified scattering for, you have a log at the phase. So this tells you that psi has a modified scattering, and this is the profile. So these are the profiles giving on rays. And so you have a better decaying portion as well. And I'm telling you at the end that we decided after computations that at the end of the day, those profiles are not independent of each other. Obviously, they couldn't be because they came together in that system. So you can relate, if you write in hyperbolic coordinates, the asymptotic profile that you get for electromagnetic potential, you can relate it to the asymptotic profiles you get for the spinor vector field. And that's how they're connected. So this is rays. That's what you mean, x over t. Those are on the rays. Yes, yes. The issue will be when you approach the boundary. That's the real issue. So that's the real issue, but they will decay enough so to kill this fast decaying thing. Yes, the cone, yeah. Nothing happens. So this will gonna decay faster. Your solution, your profile is like decaying on those rays. So it's gonna decay and it's gonna act on this that's decaying faster near the cone. So this has enough decay built in that you'll not have an issue. So you're gonna get the exact same expansion, asymptotic expansion for the electromagnetic potential as well for the spinor. So nothing really happens. So here I'm gonna comment a little bit of what has been known, and I'm gonna, so see, I divided it, I don't know how smartly I did it, but so we did local well-posedness, we looked at it, those are people that have worked in dimension equal d equals 3, and this is local well-posedness that has been done, and it grows, I don't know how to pronounce this, Burnavias, Dankoma, Foski, and Salzberg. And then I put here a lot of global well-posedness that has been done, and the one that I want, and I put it, I went between dimensions, but I want to mention something. Among all of those results, and I probably did not cover everything that has been done, and I apologize, those are the things that I looked up. So the one that gets closer to what we're doing is this Pisarelli paper on 2007. It is in dimension d equals 3, and let me explain you why I say it comes closer. So I told you that we're proving two results, global well-posedness and scattering. She made no choice in terms of gauge. She worked with the equations the way I showed you with the curvature. She made no choice in choosing any gauge. She made a statement of having her initial data being localized, which led to a simpler analysis. And somehow she did very well in terms of using as little number of vector fields and derivatives as possible, though I'm not convinced it's optimal, but it might be. So from that point of view, her result from the global well-posedness, that kind of existed, but like I said, for compactly supported initial data, we don't have that. In terms of pointwise bounds, she did have pointwise bounds, but just the leading part, so nothing in terms of getting a full expansion, a full asymptotic expansion for the equation. So this is closer to us. Then there are other works that I'm not going to mention, and then there are other ideas. And so I should say here, most of the ideas that you've seen here, we borrow from the work of and not is not written here, from the work of Tataru, Metcalf, and Marzola. And I'm going to get it. I don't know. I'm sorry. I apologize. So it's not in here, Daniel. Yeah. Hopefully, we are still friends. Yeah, we borrowed some ideas from here. And then I'm citing a lot of work. It's related, but not in what you're going to see. It's related like a far distance related. I'm going to show you in what sense I mean direct. So it matters, everything that people have done in Maxwell-Klein-Gordon and Dirac equations, but we're not going to use those tools. So I'm going to get back to, it mattered, it gave an idea, but I'm going to tell you how it's different, what we've done. So this is a lot of work that people have been doing. And then let me get to the proof. So here I'm going to prove the whole theorem. So I'm going to present the both theorems at once because it's possible. But I'm going to divide it in 4 points. So this is going to cover the both proofs. So first of all, I'm going to make some bootstrap assumption because that's how it's going to be done easily. This problem is semi-linear, but in some sense acts like a quasi-linear problem. And in quasi-linear problems, you always use bootstrap assumptions because that's how the way it's going to work. And I guess you cannot do it differently. So we're going to make this bootstrap assumption. So we're going to assume that the spinor in L6, this is, and I'm going to explain a bit why L6, and then L infinity is going to be decaying like 1 over t, and we have this constant. And so our idea will be to recover this with better constants and close the bootstrap argument. And so you might wonder why we're putting L6 and not L infinity. The reason we're doing this is it's twofold. First of all, this is better than putting L infinity. Here we are putting a bootstrap. Those are actually the control norms that are enough for us and sufficient for us to close the energy estimates. So I don't need to impose better than that. So that will be natural. So this is the bootstrap assumption, and that explains why we choose L6. Then it will be very restrictive. I will put L infinity in here and try to recover it. Now, how are we going to prove this? 4 main steps are going to be the ones that we're going to do in order to prove the theorems, both global well-posedness and the way that we prove the asymptotic expansions for the solutions. So we're going to do vector fields energy estimates, and you're going to see in a second, this is going to lead to some growth in time that you're going to see it in a second. So we have this C epsilon appearing. Then we're going to do Klein-Sobolev inequalities, which again, they're carry over, and they're going to carry over this kind of loss that you've seen in here is going to show up in the Klein-Sobolev inequalities. And then we go forward and we prove the asymptotic analysis first for Dirac. And to compensate for this loss, we need to be more precise. So we'll need a wave packets testing to actually derive the asymptotic for the Dirac. And by deriving it, we're actually going to close the bootstrap hypothesis that you've seen in here. And then once we've done the Dirac asymptotic analysis, it's easier to go and do the wave and not the other way around, the wave first and the Dirac after. And so we do the wave equation, and this is going to be something that you're going to see hopefully by the end. And it's going to be just looking at the wave equation as being a wave equation with a source term, but this is done after you have understood how you got the asymptotic for the spinor, for the Dirac equation. Okay, so now let me tell you a little bit about the vector fields bound. So we are going to assume the bootstrap assumption you just seen. So we are assuming smallness in L6 and L infinity of this kind. So it's C epsilon over T. And now once we assume this smallness, we claim that we have the following energy estimates. So here, I'm not proving just energy estimates for the solutions. I'm proving energy estimates to the solutions to which I applied both derivatives and vector fields. The right combination, like I said, no more than 3 vector fields and no more than 6 derivatives. And now we are going to get that this energy of the solution is going to be bounded by the initial data evaluated in the corresponding H0 norm. And then we are going to have this growth that you see in here, which is something bothersome, but not that bothersome, because you're going to have another tool at your disposal to actually not care about this. So how do we prove this? First of all, we're going to study the linearized equation. And so this is going to be, like Daniel said, why to work twice? That's exactly what we are doing. You work once, you use the linearized equation for your system to which you apply derivatives, then vector fields combined with derivatives. So the main portion is going to fit into the picture of the linearized equation, and then you're going to have more terms in between to which you're going to do, you're going to try to somehow bound them, and I'm going to explain in a bit how. So first of all, if I'm just going to look at no vector fields applied, I'm just going to apply derivatives. Then if I apply derivatives to my system, I'm basically going to have a main portion that looks like the linearized equation. And then the in-between terms, because you're going to have a Leibniz rule, you're going to have other terms that are not exactly like the ones you have in the linearized equation. What you do, you're going to do interpolation, the regular interpolation, and you're going to be fine, because you're going to get your energy estimates in a bit. You're going to get the time derivative of the energy less than equal than initial energy to which you apply derivatives, yeah? So, and then you do Gronwall and you are done. But what happens if you have vector fields? Then you might match the main portion of the analysis with the analysis for the linearized equation, but the in-between terms are going to have vector fields, and the vector fields are going to be time dependent. So at that point, you cannot do interpolation like the regular interpolation, so you have to be careful. So you cannot interpolate on fixed time slices, and you also have an issue because remember, we are using fractional Sobolev spaces. Remember, for A, we have fractional Sobolev spaces, H1/2, H homogeneous 1/2, cross H homogeneous minus 1/2. So then this becomes hard. How would you deal with this? So you still want to work on slices, on time slices. How would you do it? So we're going to work on something we call dyadic time slab cup domain CT. I'm going to show you a picture. And we are going to do discrete Gronwall in time. So let me show you so this is something, so to give credit, this is something that's the paper that I skipped and did not mention, the paper of Daniel, Jeremy, and Jason, where they use this kind of decomposition. So first of all, what is this? This is the CT, the red region is what we call the CT region, and we call it the cup domain because we remove this cup. This is basically, you look at this is the cone, and we foliated the cone with hyperboloids. And so in this region here, so the analysis is going to get more delicate. So we are going to actually do interpolations, and the interpolations are going to be on hyperboloids at some point. But then it's going to be an issue if this region, the size of the region is going to matter, and this becomes small. You cannot do interpolation with getting the right constants. So the way to do it is to randomly eliminate one of this. Plus, you're going to see that if you foliate, you're going to have another hyperboloid that's going to exceed this region that you've seen in here. So how do we fix this? This is the CT region. And I said something about doing Gronwall discretely. How do we fix this? We fix this, you see, we overlap those regions. We did it diagonally. So you have the blue region and you have the red region. They're overlapping, so you gain because you can now foliate everything in between, and you can do interpolation easily. And then you do Gronwall on each of those steps. And then you can close it discretely because you're going to have log T type of Gronwalls, and you're going to get energy estimates that have the time derivative of the energy estimate is going to be bounded by 1 plus epsilon times the energy that you have from the previous step. That will be your initial data that is given by the initial foliation that you had, by initial CT that you had. And so you're going to use that log t times, and then that's going to give you that growth in time that you've seen. So this is an idea that we stole from Daniel's work and collaborators. And so this is actually the setup that allows you to get those estimates, those bounds that I was telling you about, those vector fields energy bounds. And this allows you to do this discrete Gronall in time and will allow you to interpolate when you have vector fields which are time dependent. And I'm going to be careful, are time dependent, but in the way we do it, that time dependence is not going to exist anymore. So, but let me get to some important notions here that I think they're interesting, and I'm going to get into the proof in a second. So, modified vector fields for our Maxwell-Dirac. So if you look at so I lied to you in the beginning when I showed you the vector fields that you just saw, the ones that I refer to as Lorentz vector fields, because that's not the ones we are going to really work with, because they don't really commute with the linear Dirac because you have the mass now. And so the extra challenge, there are more challenges than one in a sense that, let me explain you in a bit. So if I were to, and that's pedagogic issue that I have, can I go for, so don't panic, I'm going straight to the first equation. The reason I'm doing that is I want to show you something. I'm going to apply a vector field to this, the right vector field that I modified. And so I can use the vector field that I showed you, the gamma. Where are you? And now Daniel is dizzy. So I can use any of those vector fields, omega, alpha, beta. Yeah, I can take any of them. I can apply it to my system. But when I apply it, I will see that it doesn't commute with this linear portion, with the Dirac portion. Yeah, it's not going to commute with the Dirac portion. And so that's not something that I found. Georgiev realized that you'll need more. You need to fix that omega alpha beta to add something to it such that it commutes with the linear part. And so that's the first one that I'm going to show you in a second is Georgiev that realized how to change it so that it commutes with the linear part. But then what you have to do is to take the same vector field that you took and apply it to this product. How would you apply it to this product? Because you don't have a Leibniz rule. So I'm going to have a vector field that I need to apply to this product of I multiply the electromagnetic potential and the spinor. How am I going to do it? How am I going to distribute that vector field? And that's exactly what I wrote in here. We decided. So this is going to be the vector field that Georgiev had in his paper. So you take the regular vector field that we had under the name of Lorentz vector fields, and then you are going to correct it so that it commutes with the linear part. But then it commutes with the linear part, as you can see it, I pass it over, but then I have to apply it to the nonlinearity. And I tell you that when I apply it to the nonlinearity, it's going to become this, if you pay attention here, it's a hat, here it's a tilde. It becomes a omega tilde when it applies to the electromagnetic potential. And when I need to apply like a Leibniz rule to the spinor, it's going to retransform itself into this gamma hat that is the one that it commutes with the Dirac thing. So this was something that was in Georgiev's work. Then we had to decide the first one, the hat. But this other one, we had to find it ourselves, the gamma tilde. And this is how it looks like. And it's interesting because now you're going to have Lorentz invariant vector fields, Lorentz invariance estimates. So you're not losing that. That's the only reason we went through this pain to compute those vector fields, because we did not want to lose the Lorentz invariance in the estimates. So you are not going to lose it if you use those vector fields. Now this, the whole pairs, I did not see. This, I've seen it in Georgiev. This, I did not see. We derived it. It's just a computational thing. Like I said, there were pointwise estimates derived for Maxwell-Dirac by the Pisarelli. So maybe she had it somehow, but this is probably how they look like in this Lorentz vector. She had the vector fields, but she never wrote them down, or no one else wrote them down in the Lorentz gauge. So I guess that's how they look in the Lorentz gauge. So going further, so we had the energy estimates, we had everything, and now we want to get improved vector fields bounds. So this has nothing to do with what we've done before. This has something to do with us getting better Klein-Gordon-Sobolev embeddings, estimates for the solutions. So pointwise estimates. So what do? So you see we came up with this norm, which we call it XT, in which we don't only look at the solution of the Maxwell-Dirac, but we also add the source terms and we measure them in L2. And so I should be clear here, it's L2 in space and time, and here it's L3/2 in space and time. And so to explain to you a little bit, you'll be confused why not H-1, or H, because this is not gonna, we want to avoid fractional Sobolev spaces, so we use the embedding that the L3/2 embeds in H homogeneous 1/2. So then why do we have these powers of T? This would have been, I should have measured the source term in L1, L2, but then I wanted to make it L2 both in space and time because that will be easier for the interpolation purposes. And the interpolation is going to happen in some regions where the time and space are fixed, so you don't want to discriminate. So that's why you want both L2, L2 in space and time. And if you do a Grunwald in time, a holder in time, you get T1/2, and for this other one you get T1/3. So you have this norm, and I prove and we claim that we can get, assuming that we have the bootstrap assumption holding, that we are getting on this C less than equal than T. So there are all the regions that are below this. So the overlapping ones are below the T less than equal than time. So this is the time. We have the following energy estimates holding. And again, you can see that we are getting this time growth that appears again. But that's okay because we got better control. We got more control on the source terms here, which was something that we did not have before. And you can apply those energies here. We wrote it easily. We wrote it at it looks like I'm just getting this for the solutions, but I'm not getting this for the solutions. I'm getting this for the solutions derivative vector field, so you can apply everything to it and get the same estimates as well. So now what do we do with this? We go forward because those are needed to get Klein-Gordon-Sobolev inequalities. And here I put a statement that's very general. So psi and A, they don't necessarily need to be the solution to your Maxwell-Dirac equation, actually. So I'm assuming only that I'm in the city, in the region that I showed you, the Cub region. And then I'm assuming that I have the smallness holding. So all the derivatives and vector fields, but not that many, like I said, 3 plus 6. They are smaller in this norm. I have the smallness condition. And then I'm assuming, I'm obtaining that I get these pointwise bounds in these regions, in these city regions. I'm getting that psi decays like 1/T. And I'm getting the normal derivative of the electromagnetic potential decays like 1/T to the 3/2. And the tangential derivatives decays as well, like T to the minus 3/2. And here I wrote the tangential derivative in terms of the vector fields you've seen. It's just more formally. And so how would you prove this Sobolev embedding? And I said this is actually not related to the problem because what I meant is that if you're going to use this vector fields bounds, improved ones, you see you have this growth that shows up. So if you're really talking about if you're really talking about Maxwell-Dirac system, you're going to get this T to the C epsilon times the smallness, which is epsilon. If you're going to do Klein-Gordon-Sobolev, you're going to see that growth literally popping out in here. So you're going to see T to the C epsilon times epsilon in here, and it will appear on here everywhere. So that growth still persists in this Sobolev-Klein-Gordon inequalities. So how do you prove this? So this requires some Sobolev embeddings, which, like I said, is difficult to do embeddings when you have vector fields that are time dependent. So you have to restrict yourself in a region where things are fixed. So the time is fixed, basically. And so you can do this kind of Sobolev embeddings. And so we call this city regions, CTS regions. I'm going to show you in a second. And we also need to be careful because it's not the trivial Sobolev embedding you would do. You need to use a little bit more. You need to use the linear Maxwell-Dirac equation in this XT norm that we devised. And gets more information than just the norm of the solutions, gets the information about the sources. You are treating the sources, the nonlinearity as a source in the CTS regions. And so it's not quite a classical argument, but let me explain to you what are those CTSs plus and minuses. So this is, again, work that I've seen in Metcalf, Tataru, and Tohaneanu's work. So basically, it was not enough that we diadically decompose in time in slices. We actually decompose in those rectangles, which are counting how far away from the cone you are. So the CTS minus, you are being outside the cone, and the CTS pluses, you are being inside the cone. And so just remember that S is smaller than T, and S, this matters when you do estimates, because when those are going to become larger and larger later on, you're not going to need them. So you're going to need them close to for the interior, basically, and for the exterior up to a point. In the very far away regions, you do have the right decay, so you don't need to worry about any issues whatsoever. So going back to this, improving those Kleiderman-Sobolev pointwise bounds, we actually need to get back to the energy estimates and do them better in those CTS's regions. And so here I'm going to make the assumptions that we are going to have the initial data small in L2, and then we are going to have the box in L1, L2. And so this is the source term. So we took it, here you see two portions of this term. We are talking about each equation, the wave equation and the Dirac equation separately. And so we are looking at those equations in CTSs, and basically for us, the nonlinearity is going to be just a source term. And so we are measuring this in L1, L2. We are assuming this is small. And then we are going to get the following estimates that are holding on the CTSs that I showed you. First, you get that the normal derivative, the gradient of A in this CTS is bounded by T1 half, T to the 1 half, and then you see the tangential derivative is better. It's going to be bound by S1 half, so basically S to the power 1 half. So basically this kind of analysis gives you a more control on the electromagnetic potential. It just tells you there is a portion of the electromagnetic potential that behaves better, decays better, and one that doesn't. And that's essential when you're later on going to write down the asymptotic description. And it's even more interesting when you do this for the Dirac equation. See, we put the source term L1, L2 being small. We have this initial data and the source term to be small. And so we always add this extra information that you now can control. And then we claim that we have two potential ways so our wave, it's exactly like what you've been familiar with, that the Dirac equation, Dirac solution is going to split in two, I'm going to call them in two waves that are like Klein-Gordon waves. And there are going to be one that decays better, the in one, and one that decays not that well. And so to make a picture, you are in this CTSs, which is a picture that I found very useful. So you are in those CTS regions, which are like parallelograms. And you remember, they come up with a foliation that you can make with hyperboloids of your region. So, and now you have a way to actually bound. So this will be tangential portions of your solution psi, and this is going to be the out. So this is psi out, that you have a way of, so those are like tangential to the hyperboloids. The vector fields are going to help you do that. But then you are going to have waves that are coming in, and there are more transversals, and we call them psi in, and those are going to be decaying better. And so that's what we meant by this kind of decomposition. And that also helps you understand something. Understands that comment that I made previously, that I said we're going to use the linear equation to do the Sobolev embedding, meaning that we are going to do embeddings on hyperboloids, but that will not be enough because we will need more than just knowing how the vector fields are going to be in this direction, and we cannot really interpolate in between those norms. We are going to need also a radial trace that will tell us how we are. So that's basically where we use the linear equation to derive this component. So it's like forming a base on these CTSs and make use of it to actually make the embeddings happening. So the embeddings are going to happen at the level of those CTSs, where basically you fix the time, the t minus r, the t plus r. So it's like on a fixed, the constants are fixed, so you can do like regular embeddings, regular Sobolev interpolations, embeddings, whatever you want to call them. So now this helps you to get better estimates in those regions, which in turn are going to help you get better pointwise estimates when you do Klein-Gordon-Sobolev. So you have an understanding of how those waves are actually moving. Oh my God, I need to. So here is a sketch of the proof. If you forgot anything that I said, this is the steps we followed. Now I'm going to skip this, and I'm going to show you something very interesting, which I guess you're going to, so I will finish in a second. So first of all, now we realize we have a Klein-Gordon-Sobolev, but we don't have the way we want them because we have that time growth. So we need to do something better to actually write the asymptotics down. And that's where the wave packets analysis comes into play. But let me actually say a story. So I'm going to start with the linear Dirac equation, which if you assume you have smooth localized data, you can write out that the solution to the linear Dirac is going to look like this. So you have a phase, you have a profile which decays rapidly, this rho plus minus. And we know that we do have two such profiles because we've seen from the analysis before that we have two psis which have different, the psi split in two ones, and they have different decay. So I have two such psis. I expect on array, so V is array that x over t. So I expect that on array, this is the kind of expansion I should have. This is the phase that is easy to get. And now this rho plus minus is going to decay rapidly as the velocity goes to 1 near the cone. And I'm going to make this comment. This corresponds to the half waves that are associated to Klein-Gordon equation. And so they are not arbitrary functions in C4. And so they actually belong to these subspaces that are being derived by these projections that I wrote in here, which projections have a kernel, and those are belonging to those kernels. I want to make a comment. I've been asked, how are those projections different from the Klein-Gordon projections that people, you are going to use the linear equation, you are going to go on the Fourier side, and you are going to split your solution in positive frequency, project on the positive frequency, on negative frequency, so those are your half waves. This is not the same projection, actually. This is a projection that lives on the physical space, not on the Fourier side. There are not orthogonal projections like the one you're familiar with. I think they're called pi plus, pi minus in other papers. So they're not the exact same object. Basically, and I can go into details to convince you, they look alike, but they're not alike. But when you're going to expand them on rays, on the frequency, you're going to express the velocity. So there's actually basically this projection discriminates on the velocity of the wave in comparison to the other ones that discriminates on the frequency, which is completely different story. So now, once you have this ansatz, you're going to take this ansatz, plug it in the Dirac equation, and get that. So you're going to make this, okay, what I want to say. And because I want to say the following thing. So you cannot get this funny looking ansatz because this is not accurate because your problem has a nonlinearity that depends on the magnetic potential A. So you want to be more careful. So instead of just assuming that this profile goes on rays, you're going to make it time dependent as well. So you make this expansion. This is your ansatz, which is better thought, better understood. You take this ansatz, you plug it in the Dirac equation, and put equal between the main leading portions of your equation, and then you're going to arrive at this asymptotic ODEs you have on rays. And this is something that tells you that this is an ODE that's solvable, actually. And so you don't need to worry, like Daniel was showing to you, that you need to care about this. You already know it's a scalar real electromagnetic potential. You already know it's real. You already know you have solutions. So that gives you an idea that you can find this profile rho plus, rho minus. It's solvable, and so this will give you an expansion from psi. Once you find the rho, you go back in and you're right. But these were more at the level of being heuristic about things, so you get to do things in more detail, so be more specific. So you need to take care of everything was approximate here. And now I want to make a comment that here is not going to be approximate. I'm going to finish in a second. So here I'm going to assume this is how it looks at the leading Gordon, and then it decays better. And I need to show that this approximation solution solves an asymptotic equation, which is exactly like a low DE, and something else better decaying. And once you integrate this in time, you are going to get your profile, which is something that you're after. So you're going to get your profile at infinity, and you are done. And this is going to close the bootstrap assumption that you made for psi, because this is going to encode the decay you wanted, and you are done. So this is, you're going to get this, go back in, and this tells you that psi really decays like t to the minus 3/2. And so, but how do you make that rigorous? And to make this rigorous is something that we developed together, so me and Daniel, in 2014, but we developed it for the NLS, which was easier. And so here, you have to be more careful because this is a matrix-looking thing. So I'm just going to tell you in a second what we do. We take wave packets that's localized in space at t to the 1/2, and then we get this vector that tells you the direction of this psi, and then once you have this ansatz, you're going to go through and derive. The only thing I want to mention is that how you'd actually derive this rho plus and minus. So you are going to do the inner product in C4 with the direction vector that you had, and this you are going to equal to this L2 inner product between the psi and the wave packets, the two wave packets that you have for the linear Dirac, and out of this you get the rho plus and minus, and this is exactly what you needed to close the properties that I told you about. And once you have that at your disposal, you are done. You're just going to go and do, I'm just going to leave that slide so you can read, and I'm not going to waste your time. So this is going to be something that helps you later to get the expansion for the asymptotic expansion for A. So should I say 2 words, or I think you guys are tired. So I would end here. I will leave that slide. I want to first say thank you very much, but then leave that slide if you're interested. Thank you.